What's up everyone, welcome back. Patrick here, and moving on to the next example dealing with differentiability, we have to show that this function here, this piecewise function, is not differentiable at this x value of 2. Now notice that this function, very similar to the previous function that we did. The only difference between this one and the previous one is that instead of having x here, we now have this x plus 2. That's the only difference. This function here is still the same for x values less than 2. It's x squared. It's just now this, instead of being x, it's x plus 2 when x is greater than or equal to 2. And just this little difference here is going to make the entire question, it's going to make this entire function totally different, as you'll see. So first thing I'm going to do is I'm going to graph this. So let's start with this x squared. So if I graph x squared, you know what, let's make it a little bit more steep, like that. So that's x squared, but notice that this piecewise function is x squared for x values less than 2. So notice that we're going to have 2 here, and then we're going to have that y value of 4, right, 2 squared. But it's not defined for x values greater than or equal to 2. So notice that this actually here is going to be a hole there. And then for x values greater than or equal to 2, it's going to be defined by this line, y is equal to x plus 2. Now notice that this line, y equals x plus 2, what's the y value for an x value of 2? Well, if x is 2, notice that the y value is going to be 4, which is the same y value at an x value 2 for this function here. And so what's going to happen is that this piecewise function, it's actually going to be continuous, right? Because that at that x value of 2 for both of these functions, they have the same y value of 4. So it's going to be a parabola to the left of this 2, but then it's going to be this line x plus 2, which I'll show like that, to the right of 2. And it's continuous. So that is a major difference between this function and the function from the previous video. In the previous video, because it was just x here, there was a jump discontinuity. But here, notice that this function is actually continuous at x equals 2, which is going to change the whole question pretty much. But remember, what do we got to do here? We got to show that this function is not differentiable at this x value of 2. So even though it's continuous here, remember, continuity does not imply differentiability. So we've done examples like this before where we had corners, cusps, vertical tangents, where a function can be continuous at a certain x value. Doesn't mean it's going to be differentiable at that x value. And this is going to be another case where you could have a piecewise function, it's continuous, but it's not going to be differentiable at that x value of 2. So I'm going to show you why. Now, to show that a function is not differentiable, like we've done in the previous examples, we've got to show that limit, that definition of a derivative, does not exist. So applying the parameters of this question here, we're going to have the limit as h approaches 0 of f of the a value is 2, f of 2 plus h minus f of 2 all over h. Now notice that f of 2, this part here, is equal to 4, right, from this function here when we plugged in 2, because for x values greater than or equal to 2, it's defined by this function. So that y value is 4. So this here, f of 2, is always going to be 4. But like in the previous example, this f of 2 plus h is going to be different depending on if we're approaching this h from the negative side or if we're approaching this h from the positive side. Okay, if we're approaching this h value of 0 from the negative side, notice that this value, 2 plus h, we're going to have 2 minus a very small negative, or 2 minus a very small number, or 2 plus a very small negative number, right? Meaning that this here is going to be less than 2. It's going to be very close to 2, but nevertheless it's going to be less than 2 because we're approaching this h value 0 from the negative side. So this h is going to be like negative 0.1, negative 0.01, negative 0.001. So this bracket's going to be 2 minus 0.1, 2 minus 0.001, etc., right? So it's going to be less than 2, this whole bracket. And so if it's less than 2, the function that we're going to be dealing with is this x squared here. So that means this f of 2 plus h is going to be 2 plus h squared if we're approaching this h value 0 from the negative side. However, if we're approaching this h value 0 from the positive side, we're going to have 2 plus a very small positive number, but nevertheless that entire bracket there is going to be greater than 2. It's going to be very close to 2, it's going to be greater than 2. And if the x value is greater than 2, then the function we got to deal with is this one right here, this x plus 2. So we would plug in this 2 plus h expression for this x value. So we'd end up having 2 plus h plus 2, like that. And so because of these two cases, we actually have to split up the limit at this point. So we got to split up this overall limit and show and find the one-sided limit. So as we approach the 0 from the negative side, remember that f of 2 plus h is going to go into that x squared function. So we're going to have 2 plus h squared minus this f of 2, that's always 4, all over h. And then as we approach the h value 0 from the positive side, that 2 plus h is going into this function. So it's going to be 2 plus h plus 2, this, so that's f of 2 plus h minus f of 2, which is going to be 4, all over h. And so what's going to happen here for both of these, check this out. 2 plus h squared, FOIL that out, that would be 4 plus 4h plus h squared minus 4, all over h. Notice the 4's cancel out. So we would have the limit as h approaches 0 from the negative side of h squared plus 4h all over h. Notice that we could factor out an h from the top, which would be h plus 4. Now the h's cancel out, and we could plug in, we could just do a direct substitution and plug in 0 for this h. So we would end up getting 4 for this limit. This limit here would simplify to 4, right? Because there's not going to be any constant left like we had in the previous example. That's why that other limit went to negative infinity. The constants canceled out, so we only have expressions in terms of h left. So we could factor out an h, and now we could cancel out that h in the bottom. And we could do a direct substitution because that 0 denominator is gone, and we would end up getting 4. Okay, so just save myself some room here. This limit here is going to end up equaling 4. And then this limit here is going to simplify really nicely. 2 plus 2 is 4, minus 4, that's just 0. So we're going to end up having the exact same thing that we had in the previous example, h over h, which is just equal to 1, and then the limit as h approaches 0 from the positive side of a constant, 1, it's just going to equal that constant. So this limit is going to simplify to 1. So the difference between this question and the previous one, This right-sided limit was still 1. It was the same. It's just now this, we have an actual number. Instead of negative infinity, we got 4. But nevertheless, notice that these two values are different. And because these two values are different, we're approaching different values as we approach 0 from the negative side and from the positive side. It means this overall limit as we approach 0 does not exist. And so we just showed that this function here, even though it's continuous, is not differentiable at this x value 2 because this limit doesn't exist because the one-sided limits are approaching different values. And to finish off this video, like I did in the previous example, I want to talk about intuitively why we're getting these values over here. So I already talked about this one in the previous video, but to do a quick little review, remember, what's the difference quotient doing? It's finding the slope of a line between 2 points. One of the points is the point that you are looking at. So in this case, it's this 2 and 4, this point here. And then the other point is a point that's very, very close to it because that h value is approaching 0. But if it's approaching 0 from the positive side, it means that the other point is going to be to the right of this 2. So the points are going to be here, and they're going to keep getting closer. So we're going to find the slope of the line between this point and that point, then this point and that point, this point and that point, and getting closer and closer to here, but from the right side. And so notice that no matter what point, what other point is to the right of this 2, that slope is always going to be the slope of this line, which is 1, right? Y equals mx plus b. The slope, the m value, is 1. And so that's why that, that right-sided limit here is 1. The slope between this point, 2 and 4, and then another point that's very close to it on the right side, it's always going to be the slope of that line, 1. Now, this point here, or this limit here, we got 4. What we're doing is the same thing. We're finding the slope between 2 points, between this point, 2 and 4, that we're working with. But then the other point is going to be now to the left of the 2. So if we start all the way down here, we're going to get a certain slope, and then we get closer and closer and closer. And as we get closer and closer here, the slope of the tangent on this function x squared at this x value 2 is going to be 4. Remember, before in the previous example, we had a hole. This should hit the origin. And then we had a line here. And we were finding the slope from here, from here, from here. And it was becoming more and more negatively sloped. So that's why I was going towards negative infinity. Versus here, that's not happening. What's happening is we have this point here. We got this parabola, and we're just approaching, 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 approaching. And the slope of the tangent at that x value of 2 for this parabola x squared is equal to 4. So that slope is approaching 4 as we approach that x value 2 from the left side. This is a little too steep for 4. It should be something like that. Anyway, so that's the intuition for why we are getting these two values. Nevertheless, even though we got two numbers this time, there's no positive or negative infinity. The point is that these two numbers are not the same. So that overall limit does not exist. And so this function here is not differentiable at that meeting point of 2. It's continuous, right? So that's the difference between this function and the previous one. Previous one had a jump discontinuity. This one here is continuous, but remember, continuity doesn't necessarily imply differentiability, and this is just another example of that.